There we go. So we are ready. We have up to 8 now, still missing 3, so I think we are going to start. You guys have any questions on previous material before we move on to it? Any questions on the previous material? There we go. We are in. Oh, so was that Gage asking if anybody can hear the music? Yeah, man, we have music usually at the beginning before starting class when we are waiting for the new guys to come in, or the late guys. All right, so today we are going to be talking about alternating series and absolute convergence. We start by alternating series. So what we call alternating series is a series of the kind sum and from either 1 or 0, doesn't matter, to infinity of -1 to the power n bn, where bn is a positive sequence, which means that bn is larger than or equal to 0. That's what we call alternating series. So you notice here it's first a -1 to the power n and then a bn, which technically means that the generic term of the series that we used to have is an is -1 to the power n times a positive sequence. Okay. The example, so n from 1 to infinity, -1 to the power n over n, for example. So in this case, bn is 1 over n. Sum n from 1 to infinity, -1 to the power n over n squared plus 1. Here, bn is n over n squared plus 1. So you have that -1 to the power n, and what you care about is the other part of it when you remove -1 to the power n.
I see.
Thanks, sir. So we will never carry the -1 to the power n into the calculations. We are always going to take bn, and bn is what we are interested in. If we have some -1 to the power k e to the -2k, then here you are having bk equals e to negative 2k. So you leave that negative 1 to the power k. And once you have that, you know that you have an alternating series. So these are examples of alternating series. Now, when does an alternating series converge? That's our main goal, always. So when does an alternating series converge? You have the rules. 1. You take an, you take limit as n goes to infinity of bk. And this limit needs to be 0. I'm sorry if I'm putting n, then it's k everywhere. Okay. You need to see that bk is decreasing. And that's why it was important to answer questions on sequences that are decreasing or increasing, because it's coming back in other topics. So first, you need bk is decreasing, limit of bk is 0, and there is another condition that is included in the definition, which is that that bk has to be positive to begin with for that to be an alternating series. All right. If that is the case, if you have these three conditions, then sum n from 1, or you can say k or n to infinity, negative 1 to the power k, bk converges. So the alternating series converges if you can show that the limit of bk is 0, bk is decreasing, and pk is positive, right? If any of those three doesn't hold, then you can't state using that alternating series that the series converges. But if the first one fails, then you know for sure from the divergence test that the series diverges. Okay? So this is all you have to check in that. So let's look at the three examples that I put on top here. We had sum n from 1 to infinity, negative 1 to the n over n. So an equals 1 over n. This is positive. That's good. So an equals f of n. That's 1 over n. And f prime of n is equal to negative 1 over n squared. The derivative of 1 over x is negative 1 over x squared, so that's a derivative. And this derivative is negative, which implies that an is decreasing. You need to show that. So we are good on these two. And the limit, and so this is bn, right? Not an, to make sure we keep consistency with the lecture. So bn is 1 over n, larger than 0. bn is f of n, that's 1 over n. And the derivative of that f is negative. When the derivative is negative, that means the function is decreasing, so the sequence is decreasing. That's why bn is decreasing. And then we take limit as n goes to infinity of bn. That's limit as n goes to infinity of 1 over n, and this limit is 0. And I usually recommend to actually start answering the question by this last one, just the way it's written, 1, 2, 3, right? Start by that one. Because if you find that this limit is not 0, then you can conclude using the divergence test that the series diverges, right? Not even go into alternating series. You just stop there. If it's not 0, you conclude using the divergence test that it diverges. If it's 0, then you check decreasing. If it's decreasing, then yes, you conclude. Does that make sense? So here we have that all the conditions are satisfied. Therefore, sum n from 1 to infinity, negative 1 to the n over n converges. Now, notice one thing. This is just a sequence that we have already seen in this class that we have modified a little bit. Okay, so that was negative 1 to the n over n. We used to have the sequence sum of 1 over n, which is called the harmonic series. That series diverges. But once we modify, bring in the negative 1 to the power n, we obtain a converging series. All right. Any questions on this? Now you guys tell me on example 2 here, what's going to happen? Or let's say the easiest one, example 3. Look at example 3. I'm going to write it here later on, but I'm giving you just to make sure we keep the steps here and the worked out example so you can do this example 3. And you guys let me know what you're doing, what are your steps. I asked to start by finding the limit of, first write down the bk is already given, take the limit of bk. What's the limit of bk in this case?
Would be 0.
0. E to minus infinity is 0. So limit of bk is 0. So then you find what's bk is f of k, which is e to minus 2k. What is f prime of k?
-2 to the minus 3k.
Negative 2 e to the minus 2k. That's it. And the negative shows you that it is decreasing. So bk is decreasing. So all the conditions are satisfied. Thus, the sum k from 3 to infinity, -1 to the k e to -2k converges. That's it. That's how you do the alternating series. It's kind of the easiest of the things that we have for series. Okay. Any questions on this?
Can you explain how you got that derivative?
It's like e to the ax. The derivative of e to the ax is a e to the ax. And a here is -2.
So you just keep the same exponent?
Yeah. That's how you take derivative of exponential.
Thank you.
Starting here, let me put that here. In general, what I said is you have f of x equals e to the ax. The derivative is a e to the ax.
Thank you.
You're welcome. Anything else? All right. Now let's look at the other example. You guys do this one. I wrote bn already. You find first the limit of bn. This is a positive sequence, and that's okay. Now, what is the limit of bn in this case?
Does it come out to 0 after you do L'Hopital's rule?
You can do L'Hopital's rule or what? Just do that. N over n squared. It's 1 over n. And you could do L'Hopital's rule as well. It's fine. So that limit is 0. And so you got to check the last one, which is decreasing. So Bn is f of n, which is n over n squared plus 1. And what's the derivative? How do we find the derivative of this?
Use the quotient rule.
Quotient rule, and how does that work?
Would it be the denominator times the derivative of the top minus
Which
the
is?
top?
Just
Which
give me.
that would be n squared plus 1
Mm-hmm.
minus n times 2n, so 3n or 2n squared
That's it. Mm-hmm.
over n squared plus 1 squared.
That's correct. And so this is 1 minus n squared over n squared plus 1 squared. And this thing is less than 0 for n larger than 1. If n is larger than 1, n squared is larger than 1, so 1 minus n squared is negative, so the whole thing is negative, which means that Bn is decreasing. That's it. So you have a decreasing Bn limit 0, Bn positive, therefore this converges. That's it. Now the second part of this is about the remainder of sum of alternating series. So you want to see how to put a bound on the remainder for alternating series. And the remainder is what we always define for these sequences as S minus Sn, where Sn is the partial sums and S is the sum. This is the sum, and that is the partial sum. And that's the remainder. So when you have a series, the sum of the series, which is the whole thing here, is what we call S. Sn is the partial sum up to n terms, a1 plus a2, all the way up to an. And when you take this whole thing and you subtract that, you call what is left the remainder, which is basically an plus 1 plus an plus 2 all the way to infinity. So the remaining sum all the way up to infinity, k from n plus 1 to infinity, ak. That's what you call the remainder, right? So you take that series, you chop it, you use Sn to estimate, and what is left is this, you call it the remainder. For the integral test, we had a way to put a bound on the remainder, which was the integral from n to infinity of f of x dx. That was the upper bound on the remainder. For alternating series, it's going to be a lot easier than this. We are going to just find out that the absolute value of Rn, which is the absolute value of S minus Sn, is always less than or equal to the term Bn plus 1. So it's always less than the following term. Notice that Bn is positive always. Bn is negative 1 to the power n. An is negative 1 to the power n times Bn, and Bn is always positive. All right. So this thing is always less than that in absolute value. And the reason, not going to write down the reason why here, I'm just going to explain. That plays into the decreasing that you have here. When you have the decreasing that's coming here, actually the remaining part there is going to be either Bn plus 1 minus Bn plus 2 plus minus, that's how it goes, right? Or it's going to be negative Bn plus 1 plus minus, minus. And because it is decreasing, the following terms are always going to be less than the term that is previous to it, right? So, and doing the plus minus, you're never going to be above the first term that comes after Sn. Because you're either subtracting from it or adding to the opposite of it, something that is less than it. So an absolute value, it's always going to be less than that Bn plus 1. That's the rationale behind it, okay? And so for our examples that we had here, for example 1, we have absolute value of Rn, which is absolute value of S minus Sn less than or equal. In example 1, we had, that's example 1, negative 1 to the power n over n. Bn is 1 over n plus 1. So here it's going to be 1 over n plus 1 as Bn equals 1 over n. Which means that the remainder is always less than 1 over n plus 1. That was for some negative 1 to the power n times 1 over n. Example 2, absolute value of Rn, which is absolute value of S minus Sn, is less than or equal. And in the second example that we had, that is Bk, so Bn is e to the minus 2n. So here it's going to be e to minus 2 times the term n plus 1. So that's it. It's Bn is e to the minus 2n for some, okay, from 1 to infinity, negative 1 to the k, e to minus 2k. Am I making sense here? Like 30 minutes late, maybe.
I'm sorry. I thought class was delayed.
Oh, sorry. Okay. So please later just watch the video of the first part that we had. Otherwise, it's really going to be hard because it's a new topic.
All right, I'll do that.
Okay. And so does this make sense for everybody, what we're doing right now? So what you do is in each of the problems where you'll be asked to deal with that, You just need to make sure that you write the appropriate Bn plus 1. Notice there is no negative anywhere here because, by the way, we are using absolute values here. So you can't have any negative 1 to the power n in these things. Never do that. You're taking Bn. And now the way this question is going to be used, this is kind of explaining, it's not just going to be Halo, right? That what's absolute value of Rn less than, right? The question would be, let me ask that question. Estimate the series with an error less than 10 to minus something. Here, let's say 10 to minus 5, right? Estimate the series with an error less than 10 to minus 5. Or how many terms are needed to estimate?
Move the paper down a little bit.
Yep. Thanks. How many terms are needed to estimate the series with a net error less than 10 to the minus 5, for example? So these two alternatives of the same question, whether this or that, you answer it the same way, right? So the question is about finding the number of terms or finding the value of n to make sure that the error is less than 10 to the minus 5, and knowing that the absolute value of that error, because this remainder is that error. That's what you call the error. Why is that the error? Because this is the true value you're looking for. And this Sn is what you're using to estimate that value. And the difference between the two is the error. You take it in absolute value. Because you could be less or larger than the value you're looking for. And how do we answer such a question? On example 1, for example, we saw that absolute value of Rn is less than or equal to 1 over n plus 1. So to answer this question, we just write this thing strictly less than 10 to minus 5. That's it. And we solve for n. You see that that's n plus 1 larger than 10 to the 5th. So n is strictly larger than 10 to the 5th minus 1. And if n is strictly larger than 10 to the 5th minus 1, then perhaps that smallest value of n that you need to answer the question is 10 to the 5th in this case, right? Because you want the n to be at least larger strictly than 10 to the minus 1 plus 1. And the next number, the next whole number that comes after this is 10 to the 5th. So you will need to add 100,000 terms to estimate that series to 10 to the minus 5. That's a huge number, right? To have 5 correct decimal points, you need to add at least 100,000 terms of this. That's really not a good thing, right? So that theorem guarantees that in this case, you would need 100,000 numbers. Do you understand the transition between these two? How I get to decide that I need at least 10 to the power 5? Does the explanation make sense? Because that's the most important thing.
Yeah, that makes sense.
Because we solve for n and we need We need the least value of n that satisfies that inequality, right? That's the thing. So, and this one being an integer, we need to find the integer that follows this. So we add 1 to it. And when we add 1, that's just 10 to the power 5th. Now, for example 2, so that's absolute value of Rn less than or equal, we have it there, e to the minus 2 times n plus 1. And we want this to be strictly less than 10 to the minus 5. And in this one, you know, because you have strictly less than here, you got to solve with the strictly less than, right? And in this one, what do? We apply natural log to both sides. So you get negative 2 times n plus 1 is going to be less than negative 5 natural log of 10. When we apply natural log on both sides. And we multiply by negative 1/2, so we flip the inequality. So it's going to be 5 over 2 natural log of 10 has to be less than n plus 1. And that tells us that n is at least 5/2 natural log of 10 minus 1. So technically in this class, we don't use the calculators, but let us compute this thing just to make sure I show you exactly what the right number there is, okay? This will be saying approximately equal. What is 5 natural log of 10 over 2 minus 1 approximately equal to? Can anyone compute that? Can anyone help with that? I don't.
4.7.
So you got 4.7. All right. And so if you get 4.7, that means n, which is an integer, is strictly larger than 4.7. What is the smallest integer that is larger than 4.7? Hello.
Can you repeat the question?
What is the smallest integer that is larger than 4.7?
That'd be 5.
That's 5. And that is to explain. I'm doing that actually to explain to you why I did this here, why I wrote 10 to the 5th, right? Because you get the number that you get, but you need to get the integer that is larger than it. You see that it adds a 1 on it. And now when we were doing the integral test, there is something that I wrote there as the integer part plus 1. That's what we did there, right? We took integer part of the number plus 1. Now, when you look at this number 4.7, the integer part of this number is 4, right? Okay, that's 4 and then 7.7. So the integer part is 4. That's why the answer is the integer part plus 1, which is 5. That's what we did back then. We just wrote integer part plus 1 without computing. And here I wanted to go through with the calculation to show you what that actually meant, okay? Is there any question? So here you can see the difference between this example and the other one. To have the same accuracy in both problems, here we needed 100,000 numbers. In this one, we need just 5. So we need to add only 5 terms, and after adding 5 terms, we will have 5 correct decimal points already in our estimation. That's pretty solid, right? So actually we don't need to add all those things. If I add just 5 of them, I'm already accurate to 5 decimal points. Any questions? On this, I'm ending the alternating series. So there are 2 things direct things on alternating series you will be asked about, showing that the alternating series converges. Find the value of n to make sure you have a certain degree of accuracy in your computation. Those are the 2 things that you'll be asked about. If you have any questions, please ask me now before we go into something else that will still involve at some point the alternating series, but not only, right? That is absolute convergence. Any questions? No? Okay. If no, then we continue. And we will be continuing with second part, which is absolute convergence. Part 2 of this lecture is absolute convergence. And this is the only topic in this class that doesn't put a condition on the sequence to be positive. So here, it's just any sequence. So you have any sequence and you take the sum of the terms of that sequence. No condition, no an positive, no negative 1 to the power n times bn. It's just a sum, any kind of sequence, sum of the terms of any kind of this sequence. So we say that the series converges absolutely if and only if sum n from 1 to infinity absolute value of an converges. And this is the reason why I always can encourage to answer questions on the previous topics before coming to class. Because as you can see here, right after this definition, you understand that we are back to square one. So we just take the series that we have, we put the absolute value on it, and the topic of this lecture today is over. Everything else is the previous lectures, because deciding that this series converges is all the topics that we have been covering till now. And nothing in this current lecture is going to help you for that. If you don't know how to do that, you're done. So, and that's how many topics are in this class. So they're built on the previous material. So please, again, as we are moving on, we still have a lot to do. Make sure you get the previous material before you come to class to continue. Otherwise, it's going to be harder. So the way we decide that the series is absolutely convergent is that we take that series and we put the absolute value on the terms. Now we go back to all the rules that we know and try to see which one. And that's the most difficult for this topic, because you don't know. You put those absolute values there and you got to know now what is the test that you are going to use to decide whether it converges or diverges. Now, that's first definition. And the second definition, if sum n from 1 to infinity absolute value of a n diverges and sum n from 1 to infinity a n converges, because actually we can decide that the sum of a n converges. There might be a way to do that. And then you can have a way also to decide that the sum of the absolute value diverges. In this case, then we say that the series converges conditionally. So you have something called conditional convergence, and you have something called absolute convergence. So that was absolute convergence. This is conditional convergence. And right here, you just have converges. When you just say that sum converges, you're not looking into knowing whether the sum of the absolute value converges or not. That's what we have been doing, not up to now, just deciding that it converges. Now we go one step ahead. We want to know if while this thing converges, the absolute sum of the absolute value converges also or not. If the sum of the absolute values converges, then by that first step we say it converges absolutely. If the sum of absolute value doesn't converge, and we do know that this one converges, we say we have convergence conditionally. And the third option that you have for any sequence, for any series, is that if the sum of an1 through infinity an, if you start by that and you see that it diverges, then you don't need to go to absolute convergence. So there is no absolute convergence. And because it diverges, it's also not conditionally convergent. So when you have a series from now on in this class, you have three options. Either the series diverges. So now if I give you a series in this class, you got three options. The series might diverge. It might converge conditionally, or it might converge absolutely. So it's a deeper look at the series. Instead of just saying diverges or converges, we have three options now. If it converges, we're going to look into does it converge absolutely or not. It can converge conditionally. It can converge absolutely. But once it diverges, it's over, it diverges. Right. Now let's look at the very first example that we had. That was sum. Notice that this is also applied to alternating series. So that's what I'm going to do here now. Apply it to alternating series n from 1 to infinity, -1 to the n over n. So first of all, we have already seen, we have shown that this sum, -1 to n over n from 1 to infinity, converges. We know that. We have shown that using the fact that it's an alternating series in the first part of the class. Now, second, we know it converges. Does it converge absolutely? So you take sum n from 1 to infinity, absolute value of -1 to the n over n. This is sum n from 1 to infinity, 1 over n, because absolute value of -1 to the power n, the absolute value of -1 to the power n is 1. So that's 1 over n. Now you're going to tell me, does this thing here converge or diverge? Sum of 1 over n. And this is the part where I tell you, it's now your knowledge of the previous topics. How would you decide on this? Does it converge or diverge? Sum of 1 over n. Anybody to help?
Would it converge?
Nope. What kind of series is this? What kind of series is this here?
Would that count as a P series?
It is a P series. So does it converge or diverge?
It diverges.
Why?
P is less than or equal to 1.
Is less than or equal to 1. So diverges as P series. P equal 1. So because it converges, but the sum of absolute values diverges, that's case number 2. So we say that this sum, n from 1 to infinity, -1 to the n over n, converges conditionally. Conditionally because it converges, but the sum of absolute values diverges. In example 2, we had sum n from 1 to infinity. We said we use k, -1 to the k e to the minus 2k. And for this, we have shown that sum k from 1 to infinity, -1 to the k e to the minus 2k converges. So we know this. First part of the lecture, we show that this converges. Now we look at the second piece. Does the sum of absolute values converge or not? And this sum is nothing but sum k from 1 to infinity. The absolute values in this case gets rid of -1 to the k. So that's sum of e to the minus 2k. What do you think? Does this one converge or not? And first of all, best question is, what type of series is this?
That'd be a geometric series.
It is a geometric series. And what's the ratio here? What's R?
-2.
R is what is raised to the power k.
So RBE.
What's that?
Would R equal E?
What is raised to the power k here?
E.
No. When you remove k from there, what is left?
-2.
E2? Still together, Eric?
Yeah, e to -2.
E to -2. When you remove k, that's e to -2. So r is e to -2, which is less than 1. That's why this is going to converge. Converges as geometric series and r equal e to -2. And you got to be able to identify these things. Because when the question is asked on absolute convergence, nobody tells you what rule you are going to use to say that it converges or diverges. Less than 1. And so in this example, we can see that the sum converges absolutely. So we would say that the series sum k from 1 to infinity, -1 to the k, e to -2k converges absolutely. That's it. That's how we do. Questions? Any questions? All right, if no questions, I'm gonna give you another example now that you guys are going to work on for 5 minutes. Example 3. Let's say we have sum from 1 to infinity, -1 to the n over n to the power 2/3. Now you will tell me if this thing diverges or converges conditionally or converges absolutely. So that's how the question will be stated on your test. Does this sequence converge absolutely, conditionally, or diverge? Anyone to answer? Let's go about answering this, Nicholas.
Yeah, I can answer it.
All right.
The first step that I did
Mhm.
was call out b of n as 1 over n to the 2/3.
Okay. That's positive.
And then I took the limit from n to infinity of b of n, which was 0.
All right. Then
And I took the derivative of b of n, and that came out to -2 over 3 n to the 5 over 3.
so the derivative, this is a power rule, and you have -2 over 3n to the,
5/3.
yeah, that's right. And you can see that derivative is negative because it's -2/3, and then this is a positive number as well. Therefore, you conclude
That the series is converging.
and then you would say, just say converges as alternating series, because what you're doing is because it is an alternating series. So you need to say that.
Okay.
So this converges as alternating series because those are the three things that you check for an alternating series to converge. Now, the second part is what?
Is looking for absolute convergence.
Good.
So
n from 1 to infinity, absolute value of -1 to the n over n to the 2/3. That's correct. And you get sum of, I'm still with you.
1 over n to the 2/3.
That's correct. So that's what you get. And how do you decide on this one?
I said this one converged because it was a p series that was less than 1.
When p is less than 1, how do we conclude for p series?
That it diverges.
Diverges. That's right. So you did everything right, but then you gave the wrong conclusion. So here you did that correct. So this is p series. P is 2/3 less than 1, rightly said. So diverges. Now, if it diverges, it means the sum of absolute values doesn't converge. This converges as alternating series, so the series converges how?
Conditionally.
Conditionally. Excellent. So we got examples that converge absolutely. We got an example that converges conditionally, and then I can give you a last example. Let's say we get sum n from 1 to infinity. N over n plus 1. How would you decide this one? So first step, you can get me that Bn. What is Bn here?
N over n plus 1.
That's good. Now, as I said, that's positive. Always find the limit first. What's the limit of an? of Bn as n goes to infinity?
1.
Excellent. That's 1. And how do we decide when the limit is not equal to 0? We don't even need to check that it is decreasing at this point. We know this limit is not 0. What do we conclude?
It diverges.
The series diverges by the divergence test. So the sum n from 1 to infinity, -1 to the n over n plus 1 diverges. And you say why? That's by the divergence test. And if it diverges, then it diverges. It doesn't converge. You can't check absolutely or anything. It diverges, right? Is this clear for everybody? Any questions? Right? If there is no question, then I'll say thank you for your time. We'll end here.
Thank you.
I see you guys. Thanks.
Thank you.
All right. See you.